Hello and welcome back. This will be our final module for the first topic, Science and Life, the first lectures. It'll be 1.1.5, and we'll call this Experimental Design. And here I want to introduce to you several important points beyond just the names of the variables, or the types of the variables, and the names of the groups that we learned about for single variable analysis, and emphasize some important points about experimental design. The first point, which you see on this slide here, says that we must have an experimental control. And I have already addressed this to some degree, but I really want to drive home the great importance of having a control. If we consider Francisco Redi's experiment when he covered one of the two dishes of raw meat, if we had only covered the dish, we wouldn't really know what would have happened in the absence of that coverage. And so the writhing mass of maggots was very important. Let's try another example. Suppose that we were doing an experiment on the value of a particular vitamin for children's growth. And regardless of the efficacy of the vitamin, the experimental design to tease that apart, it's critically important that we not only give children vitamins, or give them one group vitamins, but another group has to not have vitamins, so we can see what happens in the absence of vitamins. We can't simply compare it to some average growth or something like that, because individual local factors may confound the entire experiment. So once again, this last statement here is just reiterating the point that the control group of study subjects and the experimental group of study subjects should differ by only a single variable known as the experimental variable. So these two groups, the control group, which is what we're talking about here, that you must have a control, and the experimental group, they just vary by that one factor. A second very important point about the design of experiments is that experiments must be replicated. And this is unlike the experiment of Francisco Redi. You have to have a large sample size. For example, Francisco Redi, he only had one dish covered and one uncovered. That would not be adequate by the standards of modern science. Of course, Redi did his experiment far before those standards existed. But nevertheless, we can learn. And the reason for this requirement of having a large sample size, of having the experiments be replicated, is the fact that when you measure anything in nature, any natural phenomenon, there's going to be some natural variability. Everything is not the same. And we want to make sure that when we measure a difference in a scientific study, that what we're measuring is actually due to the factor being tested, the experimental variable, and not to naturally occurring variation within the population. And so in order to account for variation, scientists want to have a representative sample. And the minimum number often is regarded as something like 15 to 20 subjects. And this is in each group, in the control group and in the experimental group. And so we take data, take measurements on all of these individuals, 20 in the experimental, 20 in the control group, and we compare the averages, and we make a statistical conclusion based on that. And this is simply, if you think about it, think if we're, I don't know, giving some food supplement, say to chickens or something like that, in order to increase their growth, and this would be an agricultural study, but chickens, like many things on earth, are biological entities, and so a biological study is appropriate. The fact of the matter is, certain chickens just grow faster than other chickens, regardless of the supplement. And if you only did the experiment with one chicken in the experimental group and one chicken in the control group, and the chicken in the control group happened to be a real fast grower, and the one in the experimental group that got the supplement was a slow grower, and even with the supplement, it might grow slower than the faster growing one due to natural variability. But by having a large sample size, we would hope that we would have in the experimental group uh, maybe a fast-growing chicken, and in the control group a fast-growing chicken, and then the supplement would be on top of that. And that's why you have to have 15 to 20, so it's large enough to average out in a statistical sense. We can also explain this requirement to account for variability by doing a simple experiment, flipping a coin. And like all experiments, this experiment will require time and money. So if I flip this coin here and I get heads, so there I've done an experiment and I actually collected some data. So from that experiment, I could then conclude that every time you flip a coin, you get heads, right? Well, I did the experiment, I flipped the coin, I got heads, so I know now when I flip a coin, I get heads. Except I hope you're shaking your head saying, no, this isn't right, because in fact you do know that there's another possibility. The variation in the population of coin flips isn't huge, but you recognize that it's more than just heads, that there's also tails. And so despite the fact that we have relatively low variation in that population, we can see that we still need a larger sample to account for that variation, even with coin flips. And there's even much more variation in the natural world, and so that's why we need to replicate our experiments. So if I ask you on an exam to design an experiment, you better say that you have a sample size of 15 to 20 subjects in the control group and 15 to 20 in the experimental group. It's an important aspect of experimental design. And the third and final aspect of experimental design that I'm going to ask you to include in any experiments that you design would be the fact, not that we're going to necessarily do this, but that in a scientific experiment, that the results are analyzed using statistics. Okay, so often scientists will have two values: an average of growth rates from a population that was fed a supplement, and an average of growth rates from a population or from a group that was not fed growth supplements. And so they have to compare these two growth rates, and just because one number is bigger than another doesn't necessarily mean they're different. Now, I know that this sounds wrong and confusing, but the difference is this: there is a numerical difference and there's a statistical difference. A numerical difference is absolute, but in an experimental sense, you can have a different numerical difference and yet it will be statistically equivalent, because statistics also accounts for the variation in the natural population. And so statistics does not want a slight difference in numerical value to be confused. Let me give you an example to help you understand this. Suppose we took a measurement from two groups. Let's suppose that it was our food supplement group, and we had, and we're going to say that this is growth rate over time. Say that the average growth rate per week over time is 3.5 grams for the group with the supplement, and it's 3.2 grams for the group without the supplement, the control group. And so if these differences, these values rather, 3.5, 3.2, are very close. And so the question I would ask you is, if we did the same experiment, say with our chickens, and we're looking at the average difference in weight increase per day, I don't know if I said per week before, but it doesn't matter. The average difference, what is it? What is driving that? And so if we did the experiment again, would we get these exact same numbers, 3.5 for the supplement and 3.2 without the supplement? The answer is almost certainly we would not get the same growth rates from another sample of chickens. And so, in fact, next time we might get 3.4 for the supplement and 3.4 without the supplement. And we could even on a subsequent trial get 3.5 for the without the supplement and 3.4 with the supplement. Anyway, the point here, cut a long story short, I'm sorry, is that you can have a difference based on what you measure due to variation. So when a scientist does an experiment, they want to know, are the differences that they're measuring in their averages between the control group and the experimental group, what is driving that? There are really two major possibilities. One is the experimental variable, the thing that we're testing. In the case of the example I was using, the food supplement, is that causing a difference in weight? And the other thing that can cause a difference is natural variation. And so to tease that apart, scientists use statistics. Statistics is, in fact, not a science. It is a branch of mathematics that deals with probability. And so this is a critically important tool. We are going to use statistics for one of our experiments in lab, but we're not going to really test you on this. But when you're designing an experiment, it is critical that you would state explicitly that the results of that experiment would be analyzed using a statistical test, because in fact a statistical conclusion is one of the things that separates science from other branches of knowledge, and so it's important that you would include that. Before we go on, we have one last thing to talk about before we talk about the conclusion. And this is a concept of Occam's razor, and this is just a little graphic here which illustrates this idea. If you've seen like the movie Contact with Jodie Foster, you may have heard of Occam's razor. That's a place where it was used in popular culture. But William of Ockham was a philosopher of sorts. He was, I think, a monk. But he has this famous quote that says, "Plurality should not be posited without necessity." And the idea of Occam's razor is simply saying that the most parsimonious or the simplest explanation is likely to be the correct one. Here's a quote from Albert Einstein that also addresses pretty much the same idea. He says everything should be made as simple as possible, but not simpler. And of course, the very simplest is, sometimes we say, do KISS research, keep it simple, stupid. And this is just the idea that the most straightforward explanation is likely to be the correct one. Before we end this module, we have one last topic, and that is the limitations of science. I want you to know that although science has made huge differences for the quality of life of people, and I am a great advocate of science, I recognize that science is not the only way to learn about our world. And though I will try to continue to exhibit enthusiasm about science, I want you to know that I recognize that there are other ways to learn about our world, and that science, in fact, does have limitations. So let's just close our section on science by discussing the limitations of science. First limitation is that science cannot be applied to untestable, non-material questions. In other words, remember we said science is materialistic and it's based on the measurement and analysis of matter. If you have a non-material question with nothing to measure, that science can't really address it. And one of the classical questions here is the existence of God. Science doesn't say that there is no God. Science doesn't say that there is a God. Science says nothing. Science is mute on the subject. And so it is with all non-material questions. It has to be materialistic to be addressed by science. Secondly, science cannot make value judgments or moral decisions. Sometimes people will want to invoke the most powerful forces they can in support of their ideas, but science really doesn't make these judgments. For example, consider some important things: war, pollution, clear-cutting of forests. Science can tell us the results of such thing when used in a descriptive way or even in an experimental way, but it doesn't tell us whether it's good or bad to have war, or good or bad to have pollution, good or bad to clear cut a forest. doesn't tell us whether they should be done. And so sometimes people will use as a criticism, they will say that science is amoral, not immoral, but amoral. And that is in fact correct. Science is not moral. It's not good. It's not evil. It just measures stuff. And measurements in themselves are not good or bad. And so it's important that we recognize that. Now, scientists are people, and they're engaged in making evaluations that are moral and ethical. But they don't do this as scientists. They do it as people. Science certainly provides data about issues, as mentioned above. But the decisions that are based on societal values, ethics and morals, made with scientific data about these issues, they are not science. Here's my homage, I guess, to clear-cutting forests, a mushroom cloud, some pollution. This actually might be mostly water vapor. Here's some soldiers from World War I. And we can also say that as a limitation of science, that science can't answer subjective questions because remember, one of the attributes of science is that it is based on common perception. What is the greatest musical group of all time? The greatest piece of art? What is the true religion? Science can't answer these, although you all should know that the Eagles are the greatest musical group of all time. There is just no doubt about it. I'm not sure what the greatest piece of art or the true religion is, but I'm pretty sure the greatest musical group of all time is the Eagles. And number 4 is not really a limitation of science. It's just kind of something I tacked on, that science can be considered controversial when it explains things that were previously considered supernatural or religious. For example, the origin of humans. Of course, each different human society has its own what is called a creation myth, how humans came to occupy the planet. And when science started to discover fossils that were intermediate between apes or primates and modern humans, of course, in hypotheses and theories about the origin of humans came into being. And many people were considered this to be very controversial. In any case, that about concludes our discussion here, this module. But I do want to end on this note, and that is, of course, that the Eagles are the greatest band of all time. And notice here I've written, it's scientifically proven. You should be able to write me a short paragraph telling me why science cannot prove the Eagles are the greatest band of all time. Anyway, thank you for your attention, and we'll next learn about chemistry.